day. Welcome to this presentation about seismic data. My name is Stephanie Buttigieg. I am a student following the Masters of Information Technology program at RMIT University in Melbourne, Australia. This presentation was prepared as part of the IT Infrastructure and Security course under the supervision of Professor Ron van Schneider. Today, we will talk about seismic data to understand what it consists of, how it is collected, how it can be used, and its distribution. We take a look at the instruments used in a seismic network and a recently discovered information disclosure vulnerability, plus the possible impact on the integrity of the collected data. For this presentation, I will be referring to papers prepared by scientists from Italy, Malta, India, and the United States. These papers describe the nature and use of seismic data. As mentioned in the previous slide, I shall also talk about a vulnerability discovered by a Macedonian information security research laboratory. My first observation while researching for this presentation was the diverse nature of resources relating to seismic data and its widespread use. These factors stirred my curiosity in understanding the impact of a potential security breach on the global community. What is seismic data? Seismic data is big data, which provides a time picture of subsurface structure. The Earth is made up of several layers. There is frequent movement occurring in these layers, most of which is not noticeable. Seismometers are used to collect data of these movements, or what we commonly refer to as earthquakes. Sometimes the movements are induced, that is, not naturally occurring. An example of these is oil drilling and exploration. How is seismic data collected, processed, stored, and distributed? In their paper, Mats and his team from the Istituto Nazionale di Geofisica e Vulcanologia, Centro Nazionale Terremoti, Roma, Italy, discussed the operation of a new system for seismology, known as IDA. IDA is used as the primary tool to monitor, analyze, store, and distribute seismograms from the Italian National Seismic Network. The system was implemented following an upgrade of this network. It became operational just 16 days prior to a major seismic event in northern Italy. This event and a number of subsequent events generated a large set of data in just 40 days. The image to the right shows how the distributed network of stations in northern Italy contributed to the moment tensor automatic solution for the Emilia May 20, 2012 earthquake. The moment tensor is a mathematical representation of the movement of a fault during an earthquake, and is dependent on the source strength and the fault orientation. The data collected is stored in the CNT archive, which holds approximately 22 terabytes of data, with an annual growth of 5 terabytes. This data is freely available and shared with the European network. IDA met the expectations in terms of service continuity and robustness of the real-time acquisition of seismic data. Here we are taking into consideration that there was a major event occurring just a few days after the system became operational. However, it became apparent from the large set of data collected that accuracy in determining the location and magnitude of the event was still to be achieved. The graph on the right-hand side of the slide demonstrates the discrepancies between the epicenters as recorded by the system and the revised calculations. These discrepancies are attributed mainly to poor station distribution, human error in the revised calculations, which are due to situational pressure, and geomorphological settings of the PO plane, that is, the surface features of the area. Let us now understand how a seismic network is set up. In 2015, a study was carried out by the team at the Seismic Monitoring and Research Unit within the Department of Geosciences of the University of Malta. The scope of the study was to establish an integrated system for the evaluation, forecasting, prevention and mitigation of losses from geological hazards affecting the Sicily Channel. Malta is strategically located in the Mediterranean Sea. Although seismic activity in the area is low to moderate, active tectonic processes in the Sicily Channel are of high scientific interest and not yet completely understood. The map on the right-hand side shows earthquakes which occurred around Malta and recorded by a single station. These are indicated by red circles. The blue circles are earthquakes recorded by the Italian seismic network, which we were discussing in the previous slides. It is apparent that not all events are recorded consistently by the Malta station. Increasing the number of stations in Malta and integrating the system with the Italian and European networks would provide for a more accurate real-time seismic data. As mentioned in the previous slide, accuracy in the recording of seismic data is an important driver in the setting up of a seismic network, both from a civil protection and scientific point of view. This paper is of particular interest since it describes the physical infrastructure and choice of instrumentation for the setting up of the Maltese seismic network. Each chosen site has a seismometer, a broadband sensor, and a digitizer. The central IT system of the SMRU is responsible for the streaming and processing of real-time seismic data using web services. This system is run on a Linux virtual machine, which in turn is run on a cloud computing architecture. This setup makes the system hardware independent, as such reducing the risks of failure. The system also sends real-time notifications via email or SMS, depending on the magnitude of an event. The image on this slide shows the positioning of the 3 stations in Malta, with WDD being the main station. The graphs on the bottom right-hand corner of the slide show measurements of ambient seismic noise, as recorded by the 3 stations. So far, we have discussed seismic data generated by earthquakes and used for civil protection purposes and geological studies. However, from the paper I will be talking about next, we see that seismic events can be induced and not naturally occurring. We also see that real-time data is required to mitigate interferences in the quality of data used for scientific research, which research is not necessarily related to geological studies. This paper is written as a collaboration between the Inter-University Centre for Astronomy and Astrophysics in Pune, India, the Department of Civil Engineering at the Indian Institute of Technology in Hyderabad, India, and LIGO, Livingston Observatory in the United States. Here we read about how seismic data is used to calibrate the interferometers set up by LIGO for the interception of gravitational waves. The precision of these highly sensitive instruments can be easily affected by ground movements. In recent years, there has been an increase in seismic noise within the area where the interferometers are set up. These events are induced, that is, man-made. An example of induced events is hydraulic fracking, which is the process of horizontal drilling followed by the injection of liquid at high pressure. Accurate seismic data is required to eliminate these interferences. Seismic data is also being considered when selecting sites for future instrument installations. During the first quarter of 2020, a vulnerability was detected in the Centaur digital recorder, sometimes known as a digitizer. This instrument is a widely used data logger for seismic activity. It is portable and has removable storage capabilities, which make it ideal for use in both remote and networked environments. The Centaur has 3 or 6 channel inputs for seismic sensors. Seismic data can be streamed continuously when the instrument is connected to a network. Data can also be stored on the removable media. It is also possible to retrieve data from storage when the device reconnects to the network after downtime. The vulnerability discovered was that the Centaur fails to properly protect critical system logs, such as syslog. Tests were performed using the Java Servlet Jetty version 9.4. This version suffers from a memory leak of shared buffers. The combination of these two vulnerabilities allows unauthenticated access to the data stored and processed by the Centaur. This means that seismic data on the Centaur can be tampered with. As we have seen from the papers discussed for this presentation, accuracy in seismic data is imperative in all areas where seismic data is being collected and studied. Tampering with this data is a factor which will be most unwelcome by all areas, whether civil, scientific, or otherwise. The papers reviewed during this presentation gave us insight on the collection, storage, and use of seismic data. Seismic data is analyzed for various reasons. Amongst others are civil protection, geological interest, and in support of other scientific research. Events of a seismic nature can be both natural and man-made occurrences. Regardless of the source or reason for the collection of data, seismic infrastructures are designed and implemented with the goal of attaining accurate real-time data. Although the discussed vulnerability requires a specific setup, the instrument itself should contain restrictions to protect the data contained within. Compromised data can result in false reporting of seismic events, which can have serious repercussions on the global community. Thank you for listening to this presentation about seismic data. I hope you enjoyed it, and please feel free to contact me if you have any questions. Goodbye.